Okay, let's start with Model 7. So Model 7 is actually Ethernet switching. So though we did talk a little about this particular module prior to this period, we looked at what Ethernet is, and we said Ethernet actually helps in the connection of your LAN network. And on the IEEE, Ethernet actually is on 802.3 and 802.2. Remember we said that it actually falls on layer 2, which is your data link layer. And remember I said data link layer has two portions, the software side and the hardware side. And if you recall vividly, we said the software side is where you have the LLC, and then the hardware part is the MAC, where you have the MAC address. And then the hardware side is where actually it relates with the physical layer, and the software side relates with the network layer. So if you can still recall, we did talk about that in the previous class. So today we'll be looking at the following objective. We'll look at how the Ethernet sublayers are related to the frame field. Remember the frame, when we mentioned frame, we said the frame is actually the encapsulation of data, that's in the word, the PD of data on layer 2, which is referred to as frame. And then we say we're going to look at we're going to describe the Ethernet MAC address. Remember, MAC is media access control. The MAC address is the address you have that is bound, it's a hardware program bound on inside your NIC. So the NIC port where you plug your network cable actually contain the MAC address. And then we're going to explain how a switch builds the MAC address table and then forward frames. Usually switches build MAC addresses based on connection. If you have a typical switch and you connect more than 4 or 5 systems, what the switch does is the switch has to, in the word, build the MAC addresses of those systems where each time there's broadcast from one system to the other. What the switch does is that for 2 systems to be able to exchange information, the switch must be able to identify their MAC addresses. So that the switch uses to build up its MAC addresses. So we'll describe switch forwarding method and port settings available on layer 2 switch port. So Ethernet frame. So if you look at the diagram we had, if you still recall, we also looked at this in the previous class. The Ethernet operates in the data link layer, which is layer 2. So you can see that here, and the physical layer. So it has some extension to layer 1, which is the physical layer. If you look at it, that's why you can see here you have 802.2 and 802.3. So the 802.3 extend from the MAC portion of layer 2 down to the physical layer. So the question you now ask is that what actually is this portion from the MAC down to the physical layer, which you're seeing in this color here. Now, this blue color you're seeing here, you agree with me that it's actually from the MAC portion of layer 2 to the physical layer. It means that your cable, which is layer 1, has some relationship with the MAC, which is where you have the NIC port. And that's why the entire space here, alongside with the LLC, becomes your Ethernet. So please always note this, that your Ethernet actually compromises of your physical layer and the data link layer. So the IEEE for it is 802.2 and 802.3. That's the standard. So the 802.LAN/MAN standard, including Ethernet, use 2 separate sublayers, which you have mentioned, which is the LLC sublayer and the MAC sublayer. So that you can see also from the diagram, the right-hand side. If you look at what we have here, the MAC sublayer is responsible for data encapsulation, accessing the media that we explained. It is encapsulated into frame. And then your data encapsulation, which is the IEEE 8.3, if you recall vividly, we said is the portion from the MAC down to your physical layer. And then encapsulation include the following: your Ethernet frame. This is actually the typical architecture of the data link layer. It has a frame, it has an addressing, which is the MAC address itself, and then it has an Ethernet error detection. Remember, I mentioned the error detection, that layer 2 does error detection. So, which is also subject to the frame size. Sometimes you could have a frame size that's less than the actual required frame size, which is about 1500 bytes. So if you have less than that byte in terms of size, it can be discarded. So here, the Ethernet frame includes a frame check sequence. The frame check sequence is actually what is used at the layer 2 to detect error. So if you could recall vividly, we did say that when you have from the source, probably some binary numbers, which actually represent a particular bit of data that is meant to be transferred to the destination. If it does not match with what you have from the source, we did say it will be discarded. That is the job of the FCS here, which is the frame check sequence. And it does this with the help of the redundancy and check sequence. So always remember this, very important, that in layer 2 is where you have error detection. So the minimum Ethernet frame size is 4 bytes, and the maximum is 1518 bytes. So you can see here that the minimum is 64 bytes, and the max is this. So that means that at minimum, you must have this, and at maximum, you must have this. That's the size of the frame. And the preamble field is not included when describing the size of the frame. So if you look at here, where we have the real architecture of the frame, you can see here that the preamble is where you have 8 bytes. So it's not part of the entire size of the frame itself, in the sense that this is where you have like the checksum. And the destination MAC address is here, which is 6 bytes. Your source MAC address is also here. Remember, the frame has the trailer and the header, which actually with the data in between that form the frame itself. So your type length is 2 bytes, and then your data itself is 45 to 1500 bytes. And then your frame check sequence is 4 bytes. Remember, this is what is used to carry out the computation to be able to check if your frame or the arrival information, which is going to be in form of bit as well, is actually correlates with what is coming from the source. If it correlates what is coming from the source, it's accepted. If it is not, then completely it's not discarded. So this is just a kind of a flow to show the different category of the frame itself. Okay, and then our advice that we install Wireshark. Wireshark, of course, can be obtained from your account, your student account. You download it. Wireshark is actually used to examine the header fields in an Ethernet frame. So I think we all need to do this. Possibly I will look for an activity that you can also use to practice this, to help us to be able to use the Wireshark a lot. Even those of you who advance into cybersecurity space as well, you're going to use the Wireshark for a lot of monitoring. So I advise that you download it. It's free. It's on your NetAcad account. Download it and go to the lab for this chapter. That's module 7. And try your hands on it. If you have any issues with it, you let me know. But I will get us some labs to also address this issue. Okay. So Ethernet MAC address, the MAC address and hexadecimal is actually the MAC address of a normal typical Ethernet is actually based on the hexadecimal. We actually talked about a little about the hexadecimal. I would say these are numbers from 0 to 15. So an Ethernet MAC address consists of a 48-bit binary value. It's not, in this case, you don't have, it's just 48 bits, not up to that of IPv6, which is 128 bits, expressed using 12 hexadecimal values. So that means you have 12 hexadecimal values for it. Given that 8 bits, which is 1 byte, is a common binary group, we already know that already. And to 111, once it is all ones, automatically it is F. and can be presented as the 00 to FF. That's why when you look at the MAC address, actually maybe with modem, with laptops and all of that, you see that the way it is written for Ethernet usually is 00 column, maybe 1, 2 column, because it is not expressed in hextent, but rather in this case, it's actually expressed in, you can see here, it's expressed in 12 hexadecimal values. So actually, if you look at it in all, it's 48 bits in terms of length. So the expression is going to be in this form. So you're going to have like 00 column, maybe 1F column, and then maybe 2F in that order. So those of you actually who have been looking at the MAC address of the system, if you go to your laptop and you actually type ipconfig/all under your command prompt, you can try that. You see the MAC address of your system, you see the IP address of your system. I'll also show us that at the end of this class. Somebody should remind me so that I can be able to display that. So if you want to check the IP address of the system at any point in time, the MAC address, you just type ipconfig/all. It will display the information on the screen. So with that, you'll be able to know the physical layout of your system. The hexadecimal numbers are often represented by the values, which is preceded by 0x, which e.g. 0. You can see that 0 times 73. So you could have these all expressed for the hexadecimal numbers for the MAC address of your system to distinguish between decimal and hexadecimal values in documentation. So this is meant to distinguish between your decimal and your hexadecimal value. So it is used to do this. So you can always remember this preceded by 0x. So if you have 0x here, it's just a way to tell you that, okay, to differentiate between what your hexadecimal and what and the decimal values. So hexadecimal may also be represented by a subscript 16 or the hex number followed by an H. So please always note this when it comes to the MAC address of your system. Okay, so that you can see here from the organizational unique identifier. From this point, if you look at the entire length of the MAC address of the system, you agree with me that if you have 48 bits, if you divide it into 2, that means you're going to have 24. So what they do here is the standard. So you have more or less like an industry standard telling you that this is actually the part that is meant for the organization unique identifier. That means it is actually a set. You don't change this. What actually changes is the vendor assigned. So the vendor can actually change from this portion you're having here down to your right. That is the part that can be changed by the vendor. So that means if any vendor is producing any equipment that must actually operate on 802.2 and 802.3 under the Ethernet using the MAC address, the vendor must just work with the 24-bit part of the MAC address. So that means the first 24-bit is not what the vendor will make any changes or anything. So he's going to make changes from this. Of course, there's some regulations the same way you have it for IP addresses. Remember, I said the IANA, which is the Internet Assigned Number Authority. They actually regulate IP addresses. Same thing also when it comes to the MAC address. There's some regulation because you're going to actually make your manipulation within the last 24 bit. So you don't touch this first 24 bit. So if you look at the order of steps here, is that an Ethernet address is 48-bit address expressed in 12 hexadecimal digits, because a byte is equal to 8 bits, if you can also recall. And then we can also say that a MAC address is 6 bytes in length. Remember when you said 1 byte, you're looking at what? 8 bits. So when you multiply 8 by 6, you have 48. All MAC addresses must be unique to the Ethernet device or Ethernet interface. To ensure this, all vendors that sell Ethernet device must register with the IEEE to obtain a unique 6 hexadecimal which is the 24 bits or 3 bytes. So they must actually register with IEEE. So that means you can't just produce any equipment doing this without you registering with IEEE. So it's a kind of rule that must be followed. So an Ethernet MAC address consists of 6 hexadecimal vendor, OUI, which we refer to as organizational what unique identifier code, followed by a 6 hexadecimal vendor assigned value. So this is where once you register, they will give you your own portion, which you can now use to generate your Ethernet port. So a node 2 system must have the same MAC address. Same thing like when you're on the network, node 2 system on any particular given network must have the same IP address. And that's the reason why there must be some sort of regulation, or else people will be using the same number. So under the Ethernet MAC address, we're looking at frame processing. When the device is forwarding a message to an Ethernet network, the Ethernet header includes a source MAC address and a destination MAC address. So when any device is actually forwarding a message to any Ethernet, the one thing is that it must have the source address and the destination address of the MAC address in which it is what sending that particular message to. So if you have from the source system, maybe HI is trying to send to another Ethernet device on H4, what we're saying is that it must carry what the destination MAC address of that system that is going to receive that particular message. That's what it does. So at every point in time, it must match the source MAC address and the destination MAC address before any information is being sent. When a NIC receives an Ethernet frame, it examines the destination MAC address to see if it matches the physical MAC address. So what happened here is that, and that is stored in the RAM. Now, if there is no match, the device discards the frame. And if there is a match, it passes the frame up to the OSI layers, where the encapsulation process takes place. So remember, we said what encapsulation is. So the opposite side of encapsulation is de-encapsulation. So remember at every point in time that when a NIC receives it examines the destination MAC address to see if it matches the physical MAC address that is stored in the RAM. It means that at every point in time, there's a broadcast and information is being sent. It is actually saved inside the RAM. And the RAM is where all the MAC addresses are being saved. And then we refer to that particular storage as where you have either the CAM table or the MAC table. So if there's a match, it passes the frame up the OSI layers where the encapsulation process takes place. So Ethernet NICs will also accept frames if the destination MAC address is a broadcast or a multicast. Please let me, just 1 minute, please, let me just. Okay, thank you very much. So what we're saying here is that at any point in time that the information must be sent from the source to the destination, remember that there must be a check to be sure that the source and the destination agreed on the fact that the bits must actually be in order. And then the Ethernet NIC also accepts frame if the destination MAC address is a broadcast or a multicast group of which the host is what? A member. It means it must belong to the same domain. Any device that is in the source or destination of an Ethernet frame will have an Ethernet NIC and therefore a MAC address. This includes workstations, servers, printers, mobile devices, and routers. So what this actually means is that all these devices mentioned must have a MAC address. So you're not going to have a router. A router must have a MAC address. Your mobile device must have a MAC address. Your servers must have MAC addresses. Your printers, the same thing. So they all have MAC addresses. And actually it helps for sending information. So in summary, it means that if information was leave from point A to point B, the first thing is that the source MAC address must be known and the destination MAC address must be known before the message is being sent. If that is not known, it will be difficult for message to be sent, because on the network, those are key elements alongside with your IP address and alongside with the MAC IP address. So if you look at it, it means that the two key players for message transmission is IP address and the MAC address. Okay, so unicast MAC address. When we say unicast, we're looking at one-to-one. So in an Ethernet, different MAC addresses are used for their two unicast broadcast and multicast communication. So for unicast is one-to-one, for broadcast is when you're sending to all, and multicast communication is when you're sending to group of targeted systems. So a unicast MAC address is the unique address that is used when a frame is sent from a single transmitting device to a single destination device. So when it's sending from one system to the other, remember it is the MAC address of the source and the destination address of the MAC address of the destination device. And then the process that the source host uses to determine the destination MAC address associated with an IPv4 address is known as Address Resolution Protocol app. I repeat this again, very important, that you should also note that at every point that you hear app, it means that is when the source host uses what the source host uses to determine the destination MAC address. So before the source gets to know what the destination MAC address is, what a message will be sent, and that message is actually an app, and that app is Address Resolution Protocol. So it has to resolve. It's more or less like a kind of a process where before anything is done, the source must all of us know what the destination MAC address is, and it must know it through certain protocol. Just like, for instance, when you have a new neighbor, you can't just sit in your house and know who the neighbor is. You must go through some level of process to be able to know your neighbor's name. And so what we're saying is that before you now identify your neighbor, and so this is the neighbor's name, and then you're sending something to your neighbor, you must have for me to do some background, maybe verification through either other persons, all of that. So what we're saying is that the protocol in which you must go through to know the name of your neighbor is what we refer to as app here. So that means the app resolution itself must take place first. So app has to take place before the destination MAC address is known. So please always remember what the app is. And if it's doing that, we said the MAC address associated with IPv4 address is known as Address Resolution Protocol. That means it's doing this with the help of the IPv4. The process that a source host uses to determine the destination MAC address associated with IPv4 address is known as neighbor discovery. So in the case of the MAC address associated with IPv4, it is what neighbor discovery, but associated with IPv4, it is what known as app. So that means if it must know the destination when it comes to IPv4, you refer to it as app. If it's going to know the destination when it comes to IPv6, it's known as what neighbor discovery. So you should also note this. So the source MAC address must always be a unicast. The source MAC address must be a unicast because it's going to be one-to-one. Source MAC address, destination MAC address. Now for the broadcast MAC address, an Ethernet broadcast frame is received and processed by every device on the Ethernet line. The feature of an Ethernet broadcast are as follows. It has a destination MAC address of FFL, that means all full, which is the 48 bits. And what happened is that it floored, let me just say in summary, that each time there's going to be a broadcast, it means that when the system is sending, the system on the switch, for instance, it does not know where the destination is. So there's going to be an initial broadcast, which also will be received by every NIC port of that switch or network. And after which, once the destination is identified, then of course, remember, immediately identify the destination, because one is like when you walk into a room and you say, who is John? Everybody's going to hear you mentioning John. That's the case of broadcasting. But immediately John responds, you now know who John is. So at that point in time is when the switch takes the name of John and put in the table. In other words, now actually know that, okay, this is John. So the next time there's going to be a message that we send to John, it's not going to make a broadcast, rather it will just forward that message. So this is what happened here. So it has a destination MAC address of this, that's when it's complete. And then it floored all Ethernet switches port except the incoming port. So when it's sending for the first time, it will flood all the ports except the port in which it is being generated from, which is the source. And then two, if the encapsulated data is an IPv4 broadcast packet, it means that the packet contains a destination IPv4 address that has all ones in the host portion. This numbering in the address means that all hosts on the local network will receive all that's like the broadcast address. If you say all ones, is going to be at the point where it becomes 255.255.255, which is a broadcast address. So what we're saying here in essence is that remember that what encapsulation of the data on IPv4, once it is broadcasted, it will contain the destination of the IPv4 address. So for broadcast of MAC address, always remember this, that it will what from the source, it will broadcast to all the connected devices. And then once it is identified, it will now send to that particular one. So when it's sending to all, it is broadcast. But once it's sending from one to one, it is what unicast. And then the same also is applicable when it comes to the multicast. But the multicast is some group of targeted systems. So you can see here that Ethernet multicast frame is received and processed by a group of devices that belong to the same multicast group. So there's a destination MAC address of this, for instance, when the encapsulation data is an IPv4 multicast packet, and a destination MAC address of this when the encapsulation data is an IPv6 multicast address. So this is for IPv4, and then this is for IPv6. So this is more or less giving you some kind of relationship to tell you that, fine, if you are sending using, if it's IPv4, remember, like I said here, it's still some group of systems. So it is not all the systems that receive that message. Is only what group of certain systems. So for IPv4, you can be given an instance of this, and then for IPv6 is between maybe range of maybe 33-33 when the encapsulation data is an IPv6 multicast packet. So there are other reserved multicast destination MAC addresses. So we're just giving you MAC addresses that are actually multicast address. And for your information, these are actually reserved MAC addresses. It's not that you have to work out certain calculation. No, these are MAC addresses reserved for some particular purposes. So there are other reserved multicast destination MAC address for when the encapsulation data is not an IP, such as spanning tree protocol. So you can see we have some under reserved multicast address. So you're not going to work your head out on how to work it out. So it is flooded out all Ethernet switch port except the incoming port, unless the switch is configured for multicast looping. This is when we'll be doing STP, more or less spanning tree protocol, and configuring switches to be able to do to be able to stall frame being sent unnecessarily to all the different routes, or there's a configuration to be carried out. So I think once we get to switch configuration, I think it will really help us to understand this part very well. Because multicast addresses represent a group of addresses, sometimes called a host group, they can only be used as a destination of a packet. The source will always be a unicast. That we've said that the source will always be a unicast because you're sending from one system and maybe to another system. So because multicast address represent a group of targeted systems, they can only be used as a destination of a packet. As with the unicast and broadcast address, the multicast IP address require a corresponding multicast MAC address. Remember, when you're sending to a group of systems and you're using multicast address, it has also be to correspond to some multicast MAC address. Your IP addresses will be on the system, your MAC address must be on the system. So you can actually separate one IP address from one MAC address. So always have it in the back of your mind that when you have any device that has a MAC address, that's the device, as long as that device is on the network and must actually share information, in whichever form, either as a frame or as a packet, as the case may be. What we're saying is that it must carry both the IP address and the MAC address. Please always note this. So view the network device MAC address. In this lab, you will complete the following objective. You set up the topology and initialize devices, configure devices, verify connectivity, and then describe and analyze internet MAC addresses. For information, when you're doing this practical, they come very handy and quite easy. So all you just need to do is to check for connectivity. And how do you do that? You ping. I will also show us how you do pinging on the network so that you can text when there's connectivity between two systems. Okay. And then, like I said, if you're going to check for your MAC address, remember you can use ipconfig/all. That will help you. So the MAC address table, switch fundamentals. A layer 2 Ethernet switch uses layer 2 MAC address to make forwarding decision. So if a switch must make a forwarding decision, it must use what? The layer 2 MAC address. It is completely unaware of the data being carried in the data portion of the frame, such as an IPv4 packet, an app message, or an IPv6 packet, and enable discovery packet. Remember, we said that when it's IPv4, it's an app message that must be sent for you to resolve what the destination IP address is. And if it's an IPv6, it must use what? Enable discovery to be able to identify the destination IP address. So the switch makes its forwarding decision based solely on layer 2 Ethernet MAC addresses. These are some of the foundation information you must always know about switches. An Ethernet switch examines MAC address table to make a forwarding decision. So before a switch sends any message, it must check its MAC address table, or what we call the CAM table. CAM means content addressable memory. Before forward, unlike legacy Ethernet hub that repeat bits out all port except the incoming port. So for legacy Ethernet hubs, like I said this long ago, that it does not actually has anything to make some level of decision. What it does is that it just repeats the same bit from what is being sent from the source to all the ports except the incoming ports. When a switch is turned on, the MAC address table is empty. So if you turn the switch for the first time, it's empty. That's why the switch does not actually store MAC addresses forever. Rather, when merely you shut down and you turn it on, it will be empty. And then it will start, the broadcast processes will start all over again. And then before you know, you have the CAM table will be built. And then when you shut down again, so if you look at some scenarios, actually, in most of these universities that do CBT, and they have a lot of switches, maybe in all the halls, and all the switches are connected to the different systems. if you don't manage your broadcast domain, the challenges you run is that after a while, there will be congestion. The congestion means that the MAC table will be built such that you have several broadcasts going on. So that will actually congest the memory of the switch. And at such time, you discover that message be unreachable. Is because most of the devices you have on the network are actually switch-based. And switch is known to carry out broadcast. And because the CAM table is filled up, you'll be showing unreachable, and then until you shut down the switch and then restart it all over again, you still keep having a problem. Okay, so the MAC address table is sometimes referred to as a content addressable memory. So switch learning and forwarding. Examine the source MAC address length. So every frame that enters a switch is checked for new information to learn. It does this by examining the source MAC address of the frame and the port number where the frame entered the switch. So if the source MAC address does not exist, it is added to the table. It means that it's only when it knows the MAC address that it can forward. If it does not know, it will now add it as a new address, so that the next time it's sending, that address is already known. Okay, so if the source MAC address does not exist, the switch updates it and refresh timer for the entry. By default, most Ethernet switches keep an entry in the table for 5 minutes. Note, if the source MAC address does not exist in the table, but on a different port, the switch treats this as a new entry. The entry is replaced using the MAC address, but with the more current port number. So at every point in time, what the switch does is that it does what we call learning and forwarding. Learning in the sense that trying to know if there's a new system connected to the network, and then adding the MAC address of the new system to the MAC table or the CAM table, as the case may be, and then it treats this on and on with new devices, and that's how the MAC table or the CAM table is being built. And then here, the switch also finds the destination MAC address by forwarding. So if the destination MAC address is a unicast address, for instance, the switch will look for a match between the destination MAC address of the frame and entry in its MAC address table. If the destination MAC address is in the table, it will forward the frame out to specified port. And if the destination MAC address is not in the table, the switch will forward the frame out all except the incoming port, because at that point in time, it is not in the table. So it will carry out what we call a broadcast. This is called an unknown unicast. Okay. So if the destination MAC address is a broadcast or a multicast, the frame is also flooded out all port except the income. So always the income is that where it is originated from original. It does not send it back to it. So you could see from the diagram here, as the switch receives frame from different devices, is able to populate the MAC table. So here is what we have as a MAC table. So you can see the different systems. You can see A, B, C. D, you can see A as 00A being entered, and you can see 4 being entered. You can see at that point in time, it tells you that 2 and 3 is not known yet. So this is where the CAM table keeps you. So if 1 is going to send to B, at this point in time, it does not know what B is. It will flood it in all the ports except the incoming, which is A, and then be able to take the MAC table. So once B responds, for instance, being the destination device, it takes the MAC address of B, which is 00-P here, -B, and then put on the MAC table. So that's how the MAC table is being built. But so if you send it for the first time, it will just note it and then put it there. That's how it does the filtering process. So you're going to watch this video of how switches build MAC address table. So when you're reading through the curriculum, I would advise all that you try to watch the video and get the experience, and so that you can be able to relate it to what we're saying here. Okay. The switch speed and forwarding method. We have the way switches actually behaves. There are different types of switches. There are switches that they store frame before they send. Some do what we call cut through. As they are coming, they are being sent. And these are different designs. Those that store and send, they store for the purpose of actually doing a check to be sure that what is going to be transmitted does not have any error in it and before it is being sent. So, and some of these other switches are designed as cut, that is when it's store and forward switching. But when it's cut through switching, it means that as the guy receives the frame, he's sending it instantly, whether there's error or not. And the reason is because it's to enhance speed. So in any network topology where speed is your priority, you're not really bothered with the error that comes on the network, then you can go for cut through switches. But if in a case where you actually want to make sure that error is minimized at all costs, then you're looking at the store and forward switch. The store and forward switch actually uses the CRC, which is the cyclic redundancy check. I remember I mentioned this long before now, and that's where it does the computation to check between the source frame address and the destination address. So this is for cut through, and this is for. And then I remember we also talked about duplex and speed. Sorry, we talked about duplex, full duplex, and half duplex. But here we're looking at the speed settings. So two of the most basic settings on the switch are the bandwidth, which is speed, and duplex settings for individual port. So switches also have their own bandwidth, which is more or less the capacity of data that can be transmitted across the switch itself, which is like your throughput in some cases. So you can actually say, oh, this switch is a gigabyte port switch, is a fast Ethernet port switch. That actually determines the speed. So if you're using a fast Ethernet port switch, for instance, you don't expect that speed to be the same as a switch that is of gigabit, that has a gigabit port. So they're not the same thing. So it is critical that the duplex and bandwidth settings match between the switch port and destination connected devices. So there are two types of duplex settings used for communication on an Ethernet network. One is the full duplex, where both ends of the connection can send and receive simultaneously. And then when it's half duplex, only one of the connection can send at a time. That does not mean the other will not send. The one wants to send, the other will have to wait. And then auto negotiation is an optional function found on most Ethernet switches and NIC. It enables two devices to automatically negotiate the best speed and duplex capabilities before exchanging frame. So gigabyte Ethernet port only operate in full duplex. So once you have a gigabyte Ethernet port, you're sure it operates on what? Full duplex, not half duplex. So your duplex and speed settings. Duplex mismatch is one of the most common causes of performance issues on 10 by 100 Mbps Ethernet links. It occurs when one port on the link operates at a particular speed, half duplex, while the other operates at a full duplex. So you can see here that when one is operating at full duplex, like your gigabyte port, maybe you interface a gigabyte switch with maybe a hub or a small switch that have this, you're going to have this issue. I've actually seen where some network engineers actually do settings like without knowing the implication, using a small hub to connect with the gigabyte switch. And they thought maybe probably they're designing a network. I mean, you have some kind of issues because the speed setting is not the same. So it means that this is operating at full duplex, while the other might be operating at actually half duplex. This can occur when one of both ports on the link are reset. And the auto negotiation processes does not result in both link partner having the same configuration. So it also can occur when users reconfigure one side of the link and forget to reconfigure the other. So both sides of the link should have an auto negotiation, which is more or less an agreeable way between the two switches, or both sides should have it off. Best practice is to configure both Ethernet switches to operate at full duplex. So the both switch port as full duplex, you're sure to have better transmission. The auto MDIX is the manner in which your normal Ethernet port actually auto work with your connecting devices. For instance, connecting between devices once required the use of either a crossover straight through cable prior to this period, where if you put a straight through cable when you're connecting two systems, two similar systems, it's not going to work. But with the auto MDIX, which is media and exchange, you now discover that now you can actually connect it. It's because that negotiation process actually will take place to be able to help accept that connection. So most of these modern devices actually comes with the auto MDIX. Okay, so you have some quizzes to actually take on this as soon as we finish this. But in the long run, it means that we should be able to look at Ethernet, how Ethernet operates that link layer, the physical layer, which we talked about in summary for the two of them. That means you have two sides. That's 802.2 and 802.3, a part of layer 1 and layer 2 technologies. And the Ethernet uses the LLC and marks of layer, the data link layer, to operate. That was also mentioned. And then the Ethernet frame field, preamble, that's the architecture, start frame, delimiter, destination MAC address, source MAC address, ether type, and data, and the FCS. But these are actually what you have under the Ethernet frame itself. And then the MAC addressing provides a method for device identification and the data link layer of the OSI model. And we say it's 48 bits. So the MAC address is a 48-bit address expressed using 12x decimal digit or 6 byte. And remember, we also said that you have it in you have the first 24 bits. It's actually for the IO, and then the last 24 bit is reserved for vendors. So that means vendors can actually use that to generate new MAC addresses for their systems. And then when a device is forwarding a message to an Ethernet network, the Ethernet header includes a source and destination MAC address. So once you're able to look at this, is a summary of what should have been learned at the end of the day. So I would advise that we take the quiz and then see what our performance will be there. Any question with that? Sorry, let me bring back the slide before we move forward. Any question? Hello.
Hi, sir.
Okay.
Well, so far so good.
Yeah, but I would advise that we actually use the Wireshark to play around with this aspect of the Model 7 so that we can see beauty of it.
Please, I have a question.
Please go ahead.
We say address resolution protocol, and we have.
Okay, app, yeah.
You spoke about it as in MAC address and IP address. Am I right?
Yes, we say the app is for. Go ahead.
So what do we call the one that resolves IP address and like a website name?
The one that resolve.
IP address to a known name, like now www.baze.edu.ng.
Yeah,
DNS.
Okay. For the MAC address that resolve with the web, remember your web is on an IP address. So the IP address of the web will either be an IPv4 or an IPv6.
Yeah.
And we said, if you recall what I said vividly, I said for the MAC to learn about the destination, that's the source, to learn about the destination MAC address, it does that with the help of our app. And we say when it's app, that means it does that with the help of an IPv4. That means an IPv4 network. So that means if your website is actually maybe www.bazeuniversity.edu.ng, for instance, The next thing you need to find out is that is your website on IPv4 or on IPv6, because every domain has an IP address and must belong to a particular class, either IPv4 or IPv6. So once you note that, because if you look at those who actually do hosting, if you host website, you agree with me that your host will always make you understand your IP address. So that IP address will now be IPv4, IPv6. So if it's an IPv4, then you're actually operating with app. And if it's an IPv6 that you have, then that means you're operating with an ND, which is neighbor discovery. I don't know if you understand what I'm saying.
Oh, very clear. I just want for more explanation for all of us to understand better when we are resolving MAC to IP and when we are resolving a name to an IP address too. You know, when we do trace routes, we can we can do trace routes
to know the
of
IP
address, land us somewhere and show us the party too. We can also do trace routes of a name of like Baze University now, and it will land us to somewhere too. So I just want many of us to hear this and understand it very well from you. Thank you.
Yeah,
well,
that was a very good contribution. Thank you so much. Any other question? Okay, so I will take module 7, 8, then do some lab, maybe just one lab, and then we'll close for the day. Most of us are tired, so
we'll be used to this time. I think it's good for us.
Okay.
Yes, sir.
Yes, I'm with you.
Good evening, sir.
Yeah, good evening.
You said we could run, we could type the command ipconfig in the command prompt and find our MAC address. So I'm wondering if it's not labeled as MAC address, but because I can't see anything in MAC address.
You see,
check very well.
The physical
address, yes.
Yeah, your physical address, your MAC address.
Oh, okay. I just wanted to know.
It worked for you, right?
Yeah, I've seen it. Physical address is there.
Yeah, so can you see my screen?
Yes,
that's fine.
Yeah, so when you do ipconfig, like this,
/all.
You press enter. So you could see we did say that the MAC address is actually represented in this form of 0801-62 in that order. So it's not so if you sometimes you see your physical address, it's actually
the MAC address.
And then you okay. So you can from there also you can able to tell your you can also tell if can we see the screen, please?
Yes.
What can we see?
Morning.
You move from a list of lecture notes.
Module 8
now.
Okay, so module 8 actually, module 8 has to do with your network layer. So I remember vividly we're talking about IP address and all of that. So this is where you need to settle down to see what to do here. IPv4 and IPv6 has been discussed here. So here is how the network layer uses IP protocol for reliable communication. I must say this for the record that the whole of the CCNA1 more actually describe the OSI model. So if you see yourself coming from Ethernet to network, it's just you moving along the ladder of the OSI model. So it means that I expect every instructor to first of all take the OSI model as standard and look at the behavior of each layer first in summary before you dive into the course proper, so that it makes you understand the entire thing, because the whole of the CCNA is OSI model. Just that we're breaking it down into different modules and more explanations and all of that. So in some universities, you have professors who are professors of OSI model because I mean, that actually tells a lot when it comes to communication. So I advise that we should look at it from that angle as well, anytime we're studying the material. And so here we actually look at the role of the major header field in IPv4, the role of the major header in IPv6, and also how network device use routing tables to direct packets to the destination network. And explain the function of fields in routing table of a router. Because when we say routing table is where your IP addresses are built for all the connecting routes or destinations. So here the network layer provide, remember the network layer is at the layer 3, so you can see the position of the network layer. And the encapsulation of this at the layer 3 is actually a packet. Are we together? Are we together?
Yes, yes,
okay.
yes, yeah.
Yes.
Okay, fine. So it provides services to allow the device to exchange data, and IPv4 and IPv6 are the principal network layer communication protocol. So it's either you're talking about IPv4 or you're talking about IPv6. So the network layer performs 4 basic operations: addressing end devices, encapsulation, routing, and de-encapsulation. So addressing end devices is more or less like looking at the different IP address for the end devices, and encapsulation, like we said, is the form of data at that layer, which is packet, and then routing, and then encapsulation is when it's receiving at the last end, when the system is receiving, so it has to de-encapsulate whatever is there, so that I'm able to access the real data. Remember, when encapsulation process is taking place, it's just to add new header, trailer, and up it goes. But the main information that is carried in the process is your data. But it has to add some new information at the header, so it will change in form as it's moving from one layer to the other. So IP encapsulation, encapsulate the transport layer segment. I remember it's coming from the transport layer, which is layer 4 to 3. An IP uses either an IPv4 or an IPv6. Remember, packet to impact the layer 4 segment. IP packet will be examined by all layer 3 devices as it transfers the network. The IP addressing does not change from source to destination. So it does not change from your source to your destination. And now to change addressing, but will be discussed in a later module. What it means is the network address translation will change your address. It comes in when you are trying to translate, let's say, for instance, in your organization in Baze University, for instance, you don't have an internet. You have an intranet where all the systems are connected using your private IP addresses. The very moment you now want to announce yourself to the internet or to the World Wide Web, you now have to translate all those private IP addresses into a public domain. So what we're saying is that the process in which you do this transmission, you're going to require a NAT to do that. So it's either you're using dynamic NAT or you're using what we call a static NAT. So, but that will come in the later part of the module. And so that you can see why the address can change. So this is just to tell you that addresses can change, but it can change based on certain protocol, which is the NAT. That is when you have public IP addresses and private IP addresses coexisting on the same network. Because, of course, without a public IP address, you can't be able to browse on the internet. You can't browse on the internet until you have a public IP address. So the characteristic of an IP is that an IP is meant to have low overhead, and we describe as connectionless. So an IP is connectionless. An IP is best effort, and an IP is media independent. So when we say connectionless, we're saying an IP does not establish a connection with a destination before sending the packet. It does not do that. Remember, all you just do is just send. So that makes it connectionless. So there's no control information needed for synchronization and acknowledgement when you're dealing with the IP address. The destination receives the packet when it arrives, but no pre-notification are sent by IP. If there's a need for connection-oriented traffic, then another protocol will handle this, typically TCP at the transport layer. So IP itself does not know anything about the network. All it does do is to send from source to destination. So we're saying that it is connectionless. It is also what? Media independent. It has to do with the source and the destination. So for the best effort, being part of the characteristics of the network layer, it means that the IP is not will not guarantee delivery of the packet. An IP has reduced overhead since there's no mechanism to send data that is not received. So there's no mechanism set in place to check if it has not been sent or whatever. So an IP itself is actually, like I said, connectionless. It does not expect acknowledgement. An IP does not know if the other device is operational or if it received the packet. So it can't really tell. Media independent, it means that an IP is unreachable. It cannot manage or fix or deliver corrupt packet. So IP also cannot transmit after an error. So on its own, cannot do a retransmission. An IP cannot realign out of a sequence packet. So you could see that the IP itself doesn't have anything to do with detecting anything and correcting anything. Rather, all the IP does is identifying source and know what, in fact, just a way of assigning. So when you assign it, it's just some form of identification. But when it comes to connection, he does not even know what it's actually all about. So you might have other protocols that can aid those processes. So IP must rely on other protocols for this function. IP is independent. What we mean by that is that IP does not consign itself with the type of frame required at the data link layer or the media type at the physical layer. IP can be sent over any media type, which could be copper, fiber, or wires. Okay. So for media independent, the network layer will establish the maximum transmission unit, which has to do with network layer receive this form control information sent by data link layer. The network then establishes the MTU, which is the maximum transmission unit. And fragmentation is when your layer 2 splits the IPv4 packet into smaller units. So that is where you talk about IP being what? Independent. So IP, like for instance, IPv6 does not actually change your packet. Router goes from Ethernet to a slow one with a smaller MTU. So all these are just actually characteristics of the IPv for your network layer itself. So it means that IP is what? Independent. An IP is, media independent, an IP is connectionless, and then an IP is what? Best effort. So these are the three domains or characteristics of an IP at any given point in time. So, but let's pick one of it and see. Please, when we talk about the header of an IP address, what we're looking at is the network header has many purposes. One, it ensures the packet is sent in the correct direction. It is the header that tells if it's going to your transport layer or it's coming down to the network layer. So if you see here, you see the typical architecture of the IP header. And then it contains information for network layer processing in various fields. And then the information in the header is used by all layer 3 devices that handle the packet. So this is exactly what the IP packet header is. So when you keep hearing IP header, this is what it does. So basically, always remember that it is used to it sends the correct information, the right direction. That means it helps to tell which direction it's going to. So if it's going up the layer and knows where the destination is. The IPv4 network header characteristics is that it is in binary. That we already know that IPv4 is in binary. It contains several fields of information. The diagram is read from left to right. That's 4 bytes per line. And then if you add all the bytes, you have 32 bits. The two most important fields are the source and destination, which you must always remember. So protocol may have one or more functions, but always remember that the two most important things here is your source and what? The destination MAC address. So what you have here is a typical breakdown of the entire field of an IPv4 packet, which is actually in 4 bytes. And then looking at it, that the first 2 bytes actually helps to tell you your time to leave and protocol. Time to leave is decremented by 1. And that is why when you have a packet that is actually sent to the internet on the network, is decremented by 1. After a while, it is discarded on the internet. So you can imagine a packet that does not have a destination. The question is that how does that packet end its life cycle on the network? It does that with the help of the time to leave. So the time to leave is decremented by what? 1. It's like telling somebody your time to leave is what? Every day is -1. Every day is -1 until when the person drops. So that's exactly with the packet. So it means that the packet does not transverse through the network forever. It drops by 1 until it is discarded for packet that does not have a destination. And then the second byte is actually protocol. So it means that the second byte is the entire protocol, which actually determines the set of rules of how the packet must behave. And then the header checksum takes the entire length of the 3rd byte and the 4th byte. So if you look at it, it means that your source IP address must have a time to leave, must have a protocol, and must have a header checksum. And this is actually the entire length of an IP address at every given point in time. So here is a typical explanation to help you through this. The version could either be 4 or 6. And then the defended services is used for quality of service on the field. And then the header checksum is to detect corruption in the IPv4 header and also showing you the direction. And then the time to leave, which we have explained here, so it's decremented by 1. When it becomes 0, the router will discard the packet. And the protocol is the next protocol, which is the ICMP, TCP, UDP, as the case may be. So if the protocol is an ICMP, which is Internet Control Message Protocol, it is when you ping, for instance, when you have system A with system B, and then you're trying to send information. When you ping the IP address of system B from A, at that point in time, it's pinging. That protocol that is used to test that connectivity is referred to ICMP. And then transmission control protocol is another form of the transport layer, which can also be used to transmit your packet. And then UDP is user datagram protocol. So that's for protocol. And then for source, IPv4 must be 32-bit length. And the destination MAC address the destination IPv4 address must also be 32-bit destination address. So here, there's a video in your curriculum that I would advise that all these videos, you actually watch them so that you see how the IPv4 Ethernet packet operates and then the control information difference between the different packets. That means if you're transmitting packet on UDP and then be able to identify packet for TCP. So you must be able to differentiate between the two of them. So limitation of IPv4 there are three major limitations. IPv4 address depletion. We have basically run out of IPv4 address. Prior to now, we've been on IPv4, but still in Africa, we're still on IPv4. Having actually exhausted the portion given to Africa. Lack of end-to-end connectivity. To make IPv4 survive this long private addressing and NAT were created. So this ended direct communication with public addressing. And then increased network complexity. NAT was meant as temporary solution and create issues on the network as a side effect of manipulating the network headers. Addressing NAT causes latency and troubleshooting issues. So here we're looking at increased network complexity because when you have NAT was actually meant to take care of, in other words, as a way of managing the pool of IP addresses we have. But yet, of course, it didn't really resolve the issues. So here we're saying it was made as a temporary solution and create issues on the network as a side effect of manipulating the network header and addressing network cost, which now causes some latency and troubleshooting issues. So when you do NAT configuration, what we're saying here is that it has some effect on the header addressing, and then it causes reduction in the speed. So I think it is necessary that we know these limitations and challenges. So as those of you want to take research, you can take research from here and see how best that can be enhanced. IPv6 overview was developed by the Internet Engineering Task Force, which is the IETF. IPv6 overcomes the limitation of IPv4, so that helps to improve that. And the improvement that IPv6 provides is to increase address space. Remember, 128-bit address is far bigger than 32 bits. That you agree with me. Improve packet handling and simplify header and few fields. Eliminate the need for NAT. In IPv6, there's no need for NAT. So that means the limitation we have for NAT in terms of latency, in terms of creating some kind of issues with the header, where you have delay. So we're saying that is being taken care of by IPv6. Okay. So this is the IPv4 header field in the IPv6 packet header. Okay, and then remember each of them must always have your source address and your destination address. And then the IPv6 packet may also contain extension headers, and then provide optional network layer information. Optional are placed between IPv6 header and the payload, and will be used for fragmentation and security, mobility, support, etc. So unlike IPv4, routers do not fragment IPv6. Rather, what it does is that you still have your IPv6 as a complete process. So the video here is a sample IPv6 header in a Wireshark. So you just watch, when you watch the video, there's also a need for you to open up your Wireshark and play around with the header. So how the host route, please, this part of the course is quite actually important in the sense that this is where you begin to get used to how routers make decisions. Because your student that will going to write certification exam will configure the router using one routing protocols or the other. So it's quite important that while they try to do their configuration, they start on this note, on a very good note, to understand how routers make decisions. So host-forwarding decision packets are always created at the source. Each host device creates their own routing table. So a host can send packet to the following itself. So if a host want to test, if you want to test for connectivity, what we're saying is that a host can actually test itself to see if it actually have a connectivity or not. And what does it use? It uses a 127.0.0.0.1. So for IPv4 this is the IP address for loopback test, and then for IPv6 we use double column 1. Because this double column 1 means that you have 000 column 000. That means everything is 0000 until 1. So another way of trying to actually carry out making it reduce the IPv6 use this double column 1. So for loopback test, it is this for IPv6. That's why when you develop a website, for instance, if you're doing web development on your system, it's required that anytime you're testing the behavior of the site, you're actually using 127.0.0 as default, because that is the loopback IP address. So it's reserved, and it's a reserved IP address. The local host destination is on the same LAN, and the remote host device are not on the same LAN. So if you look at here, it is clear that PC1 and PC2 are actually on the same local host. And if you look at it very well, it's clear that they have the same IP address. But this server at the other end, which is a remote host, does not have the same. So you can say the same that the remote host device are not on the same LAN. So they are not on the same LAN. Therefore, the IP address cannot be the same. Even though you have the same IP address, for instance, because it's expected that in every LAN network, you can actually use your own private IP address. But if you use the same private address on the remote network, what we're saying is that it cannot be able to ping or connect to each other, except you make this router to carry out certain routing decisions. So it's a routing decision you configure on this router that makes the two systems able to communicate. So host forwarding decision. The source device determines whether the destination is a local or remote. So method of determination is that IPv4 source uses its own IP address and subnet mask along with destination IP address. Each time it must be able to make some forwarding decision. For the IPv6, the source uses a network address and then a prefix advertised by what local router. Okay, so for local traffic is dumped out the host interface to be handled by the intermediary devices. Remote traffic is forwarded directly to the traffic and default gateway. So what this means invariably is that your router here helps you to forward every packet that is coming from this LAN to this guy. And the same thing it does vice versa, this also to this. So what we're saying is that if it's going to do this, it's doing this with the help of the subnet mask. It means that every IP address must have a subnet mask. For class A, for IPv4 class A, for instance, is 255.0.0.0. That is the subnet mask for a private IP address for class A, as subnet mask. And for B is actually 255.255.0.0. And then for C is 255.255.255.0. That's what you have as your subnet mask. The good news is that when you now come to IPv6, it's quite that the narrative is different here. You don't come and say, okay, what is subnet mask? So your subnet mask is actually the fourth hextet. That's what you use as your subnet. So that's the difference between when I'm changing from one network to the other in IPv4. When I come to IPv6, the only way I just know is that I just go to the fourth extent and I'm good with that. So, but at this level, what I just want you to notice is that when you're teaching your students, always make them understand that the remote network cannot be able to connect with the other end network or LAN network, except some routing decisions are being made on the router. And we're going to do that in our subsequent configuration. So default gateway, we already said that the router is actually the gateway that provides that default gateway access. So a router or a layer 3 switch can be a default gateway. So the features of a default gateway is one, it must have an IP address in the same range as the rest of the LAN. So if you look at this diagram here, we're saying that this router 1, which is .1, has the default gateway, which actually also belongs to the same IP address like the other system. So it means that if you say 192.168.10.0, if you give this router interface .1, you give this system, you can give this system maybe .15, .20, as the case may be, as long as it's within pool, the same, the pool of the IPv4 plus C network. But you cannot be here and then give this router a different IP address. So what we're saying is that you maintain the same IP address and then assign the numbers accordingly from one system to the other. If you do that, that is when there's communication between this system and this router. So it is compulsory by the rule of configuration that you must assign the IP address of that LAN. So the interface of the router connected to that LAN, so that it will act as a gateway. So it is actually something you must do all the time. It can accept data from the LAN and is capable of forwarding traffic of that LAN. It can route to other networks. If a device has no gateway or a bad default gateway, its traffic will not be able to leave the LAN. So please note this, that if you put the wrong IP address and is not within the pool of a given network, like as this, then be rest assured that none of this system can actually transmit packet across this router. So it must be within the same given network. Here, a host routes default gateway. The host will know the default gateway before you send, either statically or through the DHCP. Statically means when you manually assign it, and DHCP means when you configure it to be automatic. And IPv6 send the default gateway through a router solicitation. So for IPv6, it does that through the RS, which is a router solicitation, or can be configured manually. So it's either statically or manually. A default gateway is a static route, which will be a last resort route in the routing table. So please always note this, that your router will always be, if you must configure it to be able to access the remote network, it's either you're doing it manually or you're doing it automatic, or what we call dynamically. So it's either you're using dynamic method or you're using static method, which is also like the manual method. So, on a window, route print or NetSat-R display the PC routing table. So if you want to see the routing table on your system, like as you're seated right now, if you want to check what your system, the IP address that your system has built over time, just type netstat -R. You will get the IP addresses that your system has been able to build over time. So that actually is done with the help of the app on your system. So your system itself have the IP addresses of all the connection it has so far. So you can actually test that right away and see. So let's look at the routing, how routers make that decision. So what happens when the router receives the frame from the host device? So each time the router receives a frame from a host device, so what you can see here, when it gets to the router, what we're saying is that the packet arrives on the gigabyte Ethernet port of the router R1. So R1 encapsulates the layer 2 Ethernet header and trailer. Then R1 examines the destination IPv4 address of the packet and searches for the best match in its IPv4 routing table. So what happened here is that the first thing is that the router will first of all receive the packet on this Ethernet frame, because the router itself has an Ethernet port. Remember, we said that before now. And it will what de-encapsulate. That means it will remove whatever you have as a header and trailer. Then the router will now examine the destination IPv4. That means where it is going to. and then searches for the best match in the IPv4 table. So it will look at this routing table and check to see the best match and also the best path to take. And the router entry indicates that the packet is to be forwarded to router 2. So router 1 encapsulates the packet into a new Ethernet header and trailer and forward the packet to the next hub router, which is router 2. So this is how router 1 will behave. So router 1 will, of course, say fine, I'm receiving a packet, and this packet that I'm receiving through this Ethernet Ethernet port, I must de-encapsulate it so that I can understand that this is the packet I'm receiving. And then when it does that, the next thing is to examine where it is heading to. And once it examines that, it will look at its routing table and then match it. And then the next thing to do now is to what? Send it to the next router. And then for the next router, you can be able to access that system. Because once router 2 receives, router 2 will now learn to know that what PC2 is on its own network. And then PC2 will now receive the information. So there are 3 types of route in the routing table. This route are automatically added by the router, provided the interface is active and has addresses. So when it is directly connected, it means that it can actually provide the interface and make sure that it's active. So if you connect 2 routers together, or you connect a system to router, as long as it's directly connected, we're saying that it provides that the interface becomes what? Active. So because of what it will learn about each other is, so it is very easy. That's why you must have the same IP addresses when you have 2 directly connected systems. So if you have router A connecting to router B, they must all be on the same network so that they can learn about each other immediately. And then remote, there are these are the routes the router does not have a direct connection and may be learned either manually or dynamically. For instance, if there's another router on the network, maybe router 3, router 1 cannot know about router 3 except through the help of router 2. So you always note this, very important, that the router will only learn about the remote router through the directly connected router, as the case will be here. And if it's going to learn about it, must learn about it through either route static or dynamic method. So for static route, it must be configured manually. That means you must assign the IP address yourself on your own. And then how do you assign the IP address? You can see this is router 1 and router 2. Look at this network address here. It's 192.168.10.0. The one here is 10.1.1.0. If this router 1 must be able to send all the information from PC1 to PC2, what you're going to do is that inside our router 1, after configuring the interfaces with the right IP addresses, as the case may be here, remember, you're going to say on interface G0/0/0, you assign .1, and then you might have done the basic configuration based on the given IP addresses that you're saying here. And then what do? You do IP route 10.1.1.0, which is this IP address, network address. The subnet mask is 255.5.0, and you say, okay, all of them should exit. Exit to where? They should exit at this. So you're saying that everybody that is here should exit here on 209.165.0.226. So I'm going to give us this as an assignment to do. What I actually mean here is that the first thing you do here is, please note this page very well. You will configure these IP addresses. When you configure them, assign them to the different system. Try to see if PC1 will connect to PC2. And how do you do that? You ping. If you ping and you're not able to get connectivity, we're saying that you now do static routing. And how do you do static routing? You now go to the router 1, and you say IP route. So it's a protocol, it's a command. And then you say everybody here, which is 10.1.1.0, with their subnet max, which is /24. 24 means 24 bits of ones. And 24 bits of ones in they are octets. That means 8 bits dot another 8 bits dot another 8 bits. And remember, when all the octets is filled, they are all 255. That's why you have 255.255.0. That means if you convert these decimal values to binary, you have 24 ones. That's why you have 24 here. So this is what we call slide notation. So please always note this, that when you see slash this, it's telling you the number of ones, but then when you convert them to decimal, you get the actual value. So you're saying all the network within this LAN should exit their packet on .226. Now, once you do that, automatically this system PC1 will start pinging PC2. And I hope we can do that. So, but then let's see if we finish this, go back to that diagram, and then do the configuration together. Dynamic routing protocol is when you use different routing protocols to work on that. Discover a remote network, maintain up-to-date information, choose the best path to destination, find the best path when there's a topology change. And for dynamic routing, it's either you're using RIP or what we call you're using OSPF or you're using ERGRP. That I'll also explain in subsequent modules. So we're going to see how that works without stress. So if you want to see the route, like Sir Julius mentioned, then you can do trace route as a case in good to check what the station is. But the good news here is that if you want to know the kind of routing protocol you're using on the network, all you just need to do is say show IP route. When you say show IP route, it will display the route. Tell you that you're using ERGRP, you can see the ERGRP here. You see that you're using RIP, which is RIP here, and then OSPF. At the CCNA, Cisco will always test your ability on RIP or on ERGRP or on OSPF. So that you should please look out for that. So, but we will do configuration in that direction. So this is what we have at this level. So a very quick one. I'll bring up my packet tracer. If you have yours, please do. Except there are questions, you can ask me. Then I'll pause to answer that here. So do we have any question for under this module? So we can quickly look at that before we take some practicals and then you do my assignment. So my assignment is increasing now. Sir Julius. But most of my assignment will be centered around the labs. I don't know if
that's fine.
I don't know if we are comfortable.
That was very nice. Very good. It's better with the lab.
Yes.
It's better
so
with the lab.
I'm bringing another assignment here, and I said this is the assignment I'm giving you.
Yes, the assignment on this module.
Yeah. Yes, this assignment on slide 41.
Okay.
I want you to do a static routing here.
Yes.
If you look at it, let me see if I can share this.
Yes, even
do we have any questions so far?
The second one. I have a question.
Okay, you have a question. Okay, go ahead, please. Let me see.
No, I'm asking the house question, so you can ask now.
You have a question?
Any question?
I hope we're not sleeping.
No, we are together.
Okay. So any question? Is the assignment going to be difficult for us to do?
No, the assignment is not difficult.
We'll practice and get back to you, sir.
Okay.
Yes.
I think I was going to start doing something.
Meanwhile, I will be for anybody that wants to any assistance.
Yes. What the assignment means here is let me just show you something so that I'll quickly just do some. I hope you're following. I'm trying to do connections.
Yes, we are following.
Okay, fine.
We are following.
So what the assignment is saying here is that you have this. That's what we have the 4000 series router, and then I'm trying to connect this, for instance, and it's on. Okay. So if you see, if I connect maybe 010 to 010 here, and then I have this to the 960 switch. I'm going to the 960 switch, and then you have the straight through. Let's use the gigabyte port to make it the first one, and then you also use gigabyte port here. Same thing for this switch, gigabyte port, and then you have the PC. Okay. I also want to do this. Sorry, I'm giving you more work here. So if you connect this from port 1, this switch, and then I want it now to use a wireless router. How to use a wireless router? Let's see. Okay. This guy is there. And then this port. But I actually want you to configure it so that this wireless router should connect to this PC and should be on the same IP address with this network. And then this one here, straight through to this guy here. And then you do the same thing. Okay. I hope we're following what I'm doing.
Yes.
So what I actually want you to do is that I want you to connect this device. I've taught us how to enable the wireless capability for the laptops or for systems generally. So now, if you have this kind of topology, look at what happens. Of course, you know you can always adjust it whichever way. So what we're saying is that if this guy here is on.
Please, sir. Can you hear me?
I can hear you. Go ahead.
Please, this connection between these two routers. What's the connection, sir?
Yes, that's why I said we're
between the two routers. I'm talking about router 0 and router 1.
Yeah, we're looking at this. Let's just say this.
What's the connection? Is it a fiber or?
In this case, we're using a serial cable.
Okay.
We're using a serial cable. Now, if you go back to the slide on page 41, or do I need to share that again? Okay, let's just share this so you can see. Look at this slide. You agree with me that what we have is similar to this. The only difference is that I introduced a wireless router, right?
Wireless.
Mm-hmm. But if you look at that wireless,
yes.
If you look at that wireless router that I introduced, I haven't done the connection to it yet. We'll leave that so that when you guys do this assignment, then we just configure it and then you see the beauty of it, how it works. But for now, what we'll now do now is that we'll now say we're using a class C IP address here. And then this, remember this is 10. So 10 is a class A IP address, IPv4 address. And what you have in between is actually a class C IP address, but it's public. So the question now is that how do we configure this such that the PC1 is able to talk to PC2? So if we go back to our packet tracer, what we're saying is that you should come back to your bucket tracer and label it this way. This is what I want you to do here. 192.168.10.0 /24. Do we agree? We're not there.
For router 1.
Yes.
For router
that
1.
link.
Yes, for router 1, the LAN for router 1.
Okay.
And then we have 209.165. I'm talking about the link between R1 and R2. So if I were you just follow what I have. You can be doing the same thing. So that you can bring up your system and just follow what I'm doing so that you can rest assured that you can cope with it. So
209.165.
you can actually move it around the way you want it. So 165.200.24. So 200.224. And then you have it slash what? What do you have there? /30. So if I may ask, /30 means what, everybody? It means how many bits of 1?
30 bits of 1.
30 bits of 1. So if you put them in octet of all ones, how many? What is the subnet max then? In the
256.
Who can help us?
255.255.252.
.252. Are you sure? Who can help us? Look at
it's 256.
What we have is /30. If you break 30 into block of 8 bits of 1s, how many blocks will you have? Remember, the 24 is already 3 blocks, isn't it?
Yeah.
There will be 4 blocks.
So if it's 30, how many blocks will it be?
It's short of 5 blocks.
4.
Okay, it's short of how many?
5 blocks.
2. So that's 6. When you convert that 6, which is 6 1s and 2 zeros. So decimal, what do you get? If you convert 1 1 1 in 6 places and 0 0, what do you get? Have we forgotten these things we're doing before?
$252.
252.
Yeah.
How many of us agree that it's 252?
Okay. I want to agree 252.
If you don't agree, let me know. 10.1.1. Eh? Oh, are we there?
I said our teacher is drilling us. I said it's 2. Okay, I put my mic on mute. It's 252.
Do you agree?
255.255.255.252. That will be our subnet mask /. That is the meaning of that /.
So I'm asking if the rest agree with you.
So /30 now is 252.
It's 252.
I was the one that was claiming 256, but no. Let's work
252.
There's no. It can't be above 255 now.
Yeah, it can be above. Yeah, it can be above. I understand. And so 252 actually caps it.
And from back, 1, 2. 255 minus 3 will give you 252.
Yeah. Which is it?
So do we agree with that?
Yes.
Okay. So that is taken. Reason is because when you convert 6 bits of ones, remember how we did the conversion last time. When you convert 6 bits of ones to decimal, you have 252. Okay.
Okay. Yes.
So here you now have 10.1.1.0 slash 24. Now this is what you are asked to work with. So gentlemen and ladies, if you look at this critically, it means that you're asked to use this block of IP address for this LAN, and then you're asked to use this for this two connection, that's R1 and R2. And then for the LAN for R2 is this network, which is 10.1.1.0/24. And the question now is that if we're going to assign it to this system, what you're going to do for me, the assignment I'm giving you now is that you're going to configure each of this link. And then if you look at the connection here, they are telling you that use .1 and .10. That means they say you should use .1 here. Are we following? Use .1 on this, that's the interface of this router, dot what? 1. And then they said on this PC here, use .10. Are we following? And then for this /224, that's for the connection between the two routers. They say you should use .255 and .256 because that's two usable you have.
Yes.
Use what?
225.
225 and what?
Then the other one, .226.
226. Thank you. That's what we were asked to use. Then here for the LAN of 10.1.0, it says you use .1 and .10. So that means on the router interface of R2,
.1.
You use what?
.1.
And then for the PC, you use what?
.2. .10, okay. You want us to use .10?
It's 10.
Okay.
So this is referred to as free. If you want to cancel that, you go back here and click on this to take off that. So this is when you're having it, just press escape and to reset it for you. So here, this is PC2, and then this is PC1. How many of us have done this? Are we following or we're just watching me for now?
We're just watching.
Well, we are watching.
I'm following, sir.
Well, we are watching. I'm watching for now.
Okay, thank you. Okay, so what it means that this is the configuration. And so what I want you to do now is that you go to each of these routers, like now, for instance, I'm on router 1. So I'll click on router 1, look at the connection. My connection on router 1 to this switch, let me see if the switch will label the switch, fine. The switches were not labeled, so but we will label the switch and just say this is switch 1. This is 1, and then we'll say this is what?
Switch 2.
This is switch 2, thank you. Please, everyone is going to do this, please. Do we have deadline? Do we give a deadline to this assignment? Sir Julius, or we should leave it open-ended?
No, we should give a deadline so that at least we should do this. We should submit this tomorrow.
Okay, we can submit it on tomorrow.
Yes, before the
tomorrow is too soon.
Okay.
It's too soon.
So
in fact, it's something
this is
I know it's something that can be done if you understand everything. You can do it in a 30 or 20 minutes. But tomorrow is too soon.
I will be in school tomorrow.
Okay, I will see you tomorrow, sir.
So now if you look at this is R1, this is R2. If we're going to configure R1, what I will do for us is that I will help us configure R1. Okay. And then you will configure R2. So we can end for today. I think
we have not put address on wireless router.
Yes, I said we're going to leave that for now.
Okay.
Until when everybody have submitted and sure you've done it, then I could just add that, and then we send an IP address. What I actually want to teach you, I want to teach you how to configure DAC so that you can always assign IP address.
That's good, sir.
Okay, so that means for our the laptop there, laptop 0 there and laptop 1, we will not put IP address on them now.
No, don't assign any IP address to.
We just leave it down.
So you can just leave this one the way it is. But make sure you have it in your design, because I'm going to give you another activity that will enable you build on this topology. So probably what we'll just do is that let's use this topology to build on subsequent lab activities.
Okay, so let's call this one lab 1. No, we have others before now. For the sake of what we are doing, I think we should give it lab 1. Subsequently, lab 2 will be building on
this
it.
one can be lab 2.
Yeah.
Are we okay with this?
Okay.
Yep.
So let me just quickly do this because we are really out of time, so that everybody can go back. So this is if you're on R1 and you want to configure, this is what happens. The first thing, you bring your console close to the router, and you can agree with me that what we have here is the gigabyte port.
Yeah.
And then we have the serial port. So if you look at it critically, you discover that the gigabyte port is on 00001, 000, and then the serial port is on 010. So I'll just go straight to the command line, as it were. Type N. Remember, I told you when you don't want to. If you want to go straight to the configuration, you type N, and then you type.
We are not seeing that one.
Oops. Okay, sorry. I think.
Yes, that's another.
Let me bring it now. Are you seeing it now?
Okay, yeah.
Okay, fine. Now I am actually on router 1. So I'm going to configure and say config what? Config T. Right? And then the host name is what?
Okay. R1.
R1.
Thank you. Now you're going to enter the interface, which is interface T0/0/0. Are you seeing it? And then you assign the IP address. The IP address.
So the IP address we are giving here.
We're giving 192
gigabyte.
168.10.1. So we should assign 1.
Manually assigning it, right, sir?
Yes.
Okay.
Even for the dynamic IP address, you still have to manually assign. You have to manually assign, then you now talk about routing protocol. It's a routing protocol that will either be statically route or dynamic route. But in terms of assigning IP address to routers and switches, it must come manually. You must do it this way first. So this is what is given to us, and then we're given 255.055.255.0 as a subnet mask. Are we okay with this?
Yes.
That's 266.
255.
You type
255, right?
.0.
Are we okay with this?
That's mask 24.
So this is the subnet mask given to us.
For the router?
Yes, to assign to the router. That's a LAN router facing switch 1.
Okay.
Then you press enter. Then the next command is no what?
No shutdown.
No shut.
Either you say no shutdown for full or no show. That's
No shutdown.
yeah, and then you press this, and then the interface is up immediately.
Okay.
So then you can actually do a description. Are we together?
Yes.
So you can say LAN LAN 1.
Has the LAN been named?
Or LAN switch 1. Are you seeing it?
Description LAN 1.
Yes. Yes.
Do we go
Description
with
LAN
LAN switch 1
and
or
switch
LAN
1.
1?
Because
So
we can also attach another switch.
we don't
somewhere.
need to. So you're saying we can name we can call it like that without naming the LAN.
No, you have named it. You are
I'm
telling us
giving a
that this.
description, and I said, can we just
not the name.
describe that link?
Okay.
So,
So this description LAN switch 1 now is naming this router's network.
Exactly.
Interface.
LAN 1, because that is the router now. That is the LAN network from the router. You know,
Yeah. So
so I'm trying to give the description to that.
we are giving it this name.
Yes.
Okay.
So that is it. Once you do that, it's fine. It's taken. So you see, instantly there's a instantly you see that the green distance will come up. It just become green instantly to tell you that there's already what an extension going on and it's connected. So the next thing here is that on the same R1, you're meant to give this portion of R1 is what? .25. Thank you very much. So I'm going to assign that same interface. So you want the interface S0/1.
We're not seeing it.
Really? Okay. I think you're right.
You are on the other slide.
Yeah. Let me just quickly do this. So we said we'll now configure the interface of the router. Are we together? So it will be interface S0/1/0. Do we agree?
Yes. No. Okay. Yes, that's the interface we are going to now. Yes, that's the interface.
Yes. So once you enter that, you press enter. Always note this.
So we give it
the
IP address.
IP address. So the IP address will be what?
I think it's 209. Well, what do you give us?
209
/1.
165. .200. .224.
225.
This is an assignment now.
224 is a network address.
This is an assignment. You are assigning this IP address now.
Yes.
Yes.
Okay.
And the subnet mask will be what? 255.255.255.
252.
Yeah.
Yes.
Okay. So if you look at it, the reason why we're using 225 is because that's what they say we should assign on this interface. The next physical IP address. So you press this and then you say no show.
No short.
Yeah, no shutdown. You see that interface is there. So the next thing is that once you do this, when you now configure for R2, you do the same thing. So a quick one for R2.
But have we saved our information to MVRAM?
Okay. We're not done. So if you want to, I hope you're saying I hope you're saying it.
Yes.
So if you want to save to NVRAM, remember you have to end this. And then you do that at the previous exec mode, which is copy what?
You can do copy running to.
Yeah, you can do copy running config, startup config. Or you do copy run start.
Okay,
Once you do that, that's it. So if I were you can just write that command down so that you don't forget. Okay. So copy run start is to save the configuration. So once you do that, it shows that you are done with, for now, just for now, it's just a way of trying to say you're done with. So for router 2, everyone, you go to router 2 and do the same thing.
Yes.
Are we following?
Yes.
Very well.
So I'm actually going to stop here. It's already getting late, so I just want to. So this is what you do for me. We'll finish this immediately we come in the next class. So I'm just want to give you lab work to do as we go. But remember, you're owing me one lab that you have not submitted. Only 2 persons submitted. And
okay,
for the others to submit there. So
we are owing you, sir.
Okay, thank you. So you've done R1, where we're able to assign the IP address for the gigabyte port facing the switch, and we are also done for the serial port. Now you are going to do for R2 and do the same thing for both sides of R2. Once you do it, try to be on PC1 and ping PC2. But let me just show us how this pinging thing works so that you don't begin to wonder what's happening. Now, if you look at my diagram here, this is PC1, agree. Hello, can we see diagram?
Yes, sir.
I'm not seeing your cursor.
Are you seeing my console now?
No.
You can't see my console.
Your cursor has not changed.
Oh, really?
You are on command line.
Okay.
Are you seeing it?
Where are you?
Okay, yes.
Okay, we
now-
are seeing your cursor moving.
Okay, fine. They said you should assign .10 on this system. If you click on the PC1, PC1 will open its own dialog box, and they expect you now to configure that dialog box. So once you double click on PC1, this is what you see. So you go to desktop on PC1, and then click on IP configuration. Then you come to this one and you say what? 19 what?
192.
Thank you.
Dot
168. Dot 10.
Dot 10. Dot 10. Dot 10.
168. Dot 10. Dot 10. Thank you.
Dot 10.
Then the subnet mask is this.
255.2. Yes, that's.
Then what is the gateway?
So we have to
what is the
put
gateway? Default gateway.
With the router.
the address of the router.
Why? Which is what? 192.168.10.1.
Dot one.
God bless you. Now this is the IP address of the router. Now once you do that, you close that. Then there's something you're going to do also for me quickly. If you do that one, then you now look at that topology again. It's quite that there's a PC2 here. Are we saying PC2?
Yeah.
PC2, yeah?
Yes, yes.
PC2 is going to be 10.1.1.10.
Yeah.
10.
Good. So what you do is that you also do the same thing. You go to PC2. Okay. So you go to PC what? 2.
PC2.
Double click on PC2, and then
Go to desktop.
you go to the desktop.
But we are not seeing your. You know,
Can you
you
see that
are still
now?
on the.
Okay. Okay,
And then
desktop.
you click on desktop, and then
IP
you go
config.
to IP config.
IP config. And
And
we
then
do
you
the
say
same.
10.1.1.1.
10.1.1.10.
10.
10.
Yeah.
Good. And then the subnet mask is what?
255.255.255.0.
And then what's the gateway?
Then the gateway. The gateway is going to be 10.1.
10.1.1. what?
1.
One.
Thank you. That's the gateway. Now, this is what happens, everybody. Now, I want you to look at something here. If I go back to my topology as it were, which you can see, and then
You think.
can we see topology?
Yes.
Yes.
Okay, fine. If I go to PC1, I click on PC1. If you can see the PC1, can you see the interface here when you double click on PC1?
Okay.
Then you go to command prompt, the command prompt of the PC. Can you see the command prompt of the PC?
Okay.
Yes.
If I say I want to ping from PC1, I want to ping PC2. Now PC2 is on 10.1.1.10. Agreed.
Yes.
If I press ping, you can see something here. It's saying destination host unreachable.
Unreachable.
Now, this is what I now wanted all of us to get to. Now, once you get here, it means that something is wrong somewhere. What is simply telling you that you have not established an IP route. Are you following what I'm saying?
Yes.
Yes.
It means that you have not told this router to what kind of how to route everybody here to be able to see this guy, or how this guy here will be able to send their packet. Remember something here, that we said routers within the same domain will be able to see each other. So if I put another PC here and I assign .9 to it, to this switch one, and I ping this one, it will ping because they're on the same LAN. Are we following?
Yes.
But if I say this PC1 should ping PC2 across the remote network, it is not possible until you apply either static route or dynamic route. So what I want us to do now, is that,
now we can ping .1.
no.
We can ping the gateway. We are on the same.
You can ping the gateway.
Network.
You can ping the
Because
gateway of
router
router 1,
network.
it will ping. But you cannot ping the gateway of router 2.
Not, no, we cannot.
Good. So now if I say, for instance, now, let's ping the gateway. Can you see this?
Yeah.
Now you don't say you want to ping the gateway of the router. You say ping what?
192.
So the gateway of where we are.
It will ping.
192.168.10.1.
Good. Now, because they are on the same network, won't it ping? You can see it's replying.
Yes.
Now, once you see it reply from this to this, it means that it's actually displaying the information. That means there's some kind of, the ICMP is working. It means there's a response from the router. So please, everybody, what you're going to do for me now is that as part of your assignment, you're going to end up configuring the entire topology and then apply the IP route. And then when you apply the IP route, now see if your PC1 can be able to ping PC2. So we want this submitted when? Or do you want me to finish this? Do you want me to finish this in the next class and then give you another one?
We should submit this by tomorrow evening, before tomorrow evening.
Okay. So do we all agree on this?
That's okay.
Okay, please. I just want to try your hands on it. If you have any challenges, I'm here to.
No, it's better we do it little by little before it becomes cumbersome.
Yes. And that's the reason why I'm saying take your time and do this and let's see.
Yes. Yes, one step at a time.
Julius.
To happen. Sir?
You catch me up.
I said, come to school tomorrow.
Okay, sir. Okay, sir.
So,
Mr. Julius, I'll come too because please, it seems I'm kind of far, like behind.
Who is that? Is that Khadija?
No, it's Rukaya.
Rukaya, what time should we put? Oh, let's let our teacher go. Teacher, good night, sir. Thank you. Okay, Ruki, just let's meet tomorrow. Tell me when you want to come.
Okay.
So everybody, you can screenshot the topology here so that you can do that, or when you are watching the video.
We'll watch the video. Please remember to send the video as soon as we finish the class.
So I'll send it immediately so that those who want to go through it can go through. And then,
yes, sir.
Thank you for your
flexibility.
Okay.
Thank you for your flexibility.
Yeah, thank you too for.
Thank you very much, sir.
Yeah, thank you.
Thank you for your flexibility. We shall repent and come into class early. For those who
oh, Allah, thank you so much.
I'm pleading on behalf of those that came late.
Oh, Allah. And those who
okay,
are not able
good
to
night.
I'm number one on that list.
That's what I'm pleading for you.
Okay, so see you guys tomorrow then.
Thank you.
Thank you so much.
Thank you, guys. Thank you.